Well, welcome to this online revision session for AQA M2, in which we will be considering the January 2010 question 7 on circular motion in the vertical plane. In this particular problem we have a smooth hemisphere of radius A, centre O, and we have a particle of mass m which is free to move on the surface, so it's on the outside surface of the hemisphere. The particle is placed at A at the highest point and set in motion with a speed of u. So initially this is pushed horizontally with a speed of u. First part of the question says, while the particle is in contact with the hemisphere, OP makes an angle theta with the vertical, as shown in the diagram, and we got to show that the speed of the particle at P is given by this expression. So what we need to do here is to apply our use of energies. We know the initial kinetic energy in terms of u. We know the radius here is A, so we know both the kinetic and the potential energy at this point. Similarly, we can find the kinetic energy and the potential energy at this point as well. And then from those we can use conservation of energy to enable us to determine the expression required for the speed v at this point. So we're assuming here that at this point it's moving with the speed of v. Okay, so let's have a look. So at A we have a kinetic energy which is equal to a half mu squared. At B we have a kinetic energy which is equal to a half mv squared. Now we need the gravitational potential energy. Now we've got two ways we could do this. We could either take the origin O as being our zero level, or we could take A as our zero level. It's totally up to you as to which one you do. I'm going to take O and say that the height at A is little a, that's the radius of the circle, so that becomes mga. Then the gravitational potential energy at B is going to be this height here, which is going to correspond to A cos theta. Yeah, because if I dot a line across here you can see that height is the same as this one. So if this is length A, this is the adjacent length, so it's A cos theta. So this becomes mga cos theta. So we can then say that by conservation of energy that a half mu squared plus mga equals a half mv squared plus mga cos theta. Well, you can see the mass now disappears out through this expression, through here. We can multiply everything by 2 to get rid of the halves, and we will get then v squared will be equal to u squared plus 2ga, and then the ga cos theta will come across this side and give us minus 2ga cos theta. And so you can see the 2ga is a common factor in those two terms on the right hand side, and to square root it then will give us v, so v becomes u squared plus 2ga 1 minus cos theta all squared. In other words, the required result. Well, 5 marks. You're going to get a method mark at this point, and for getting the kinetic energies and the potential energies correctly will give you an accuracy mark. For then using excuse me, conservation of energy to obtain your expression through here, give you a method mark, and again an accuracy mark there, having the appropriate heights, and then finally an accuracy mark for that working through down to the required result. Now, part B of the question, it says the particle leaves the surface at some angle phi, and you've got to find out the cosine of phi, sorry, not phi, alpha, in terms of AU and G. Now, wherever this is on the surface, there is a normal reaction pushing up against that, and the weight is acting down in this direction. So we know that to maintain the circular motion, it is the component of the weight acting towards the centre of the circle that will be acting against the normal reaction. And it's that that maintains the circular motion. So the component of the weight acting towards the centre, we know, is mg cos theta. The normal reaction is in the opposite direction, and those two things together create the force towards the centre of the circle, which in this case is going to be mv squared over r, and r is the radius of the circle, which is a. So that's using the components of the forces towards the centre of the circle, creating the circular motion. Now, when will it leave contact? Well, n can never be negative. When n is equal to 0, that's the point at which it will leave the surface of the hemisphere. So when n is equal to 0, it will leave the surface. And that happens at the angle alpha. So that's at the point where theta is equal to this value, alpha. So if n is 0, that is now telling us that mg cos alpha is equal to mv squared over r, which is equal to a, the radius of the circle. But we also know that v squared was given by that expression in part A, so we can rewrite this as mu squared plus 2ga 1 minus cos alpha, and that was to the power of a half, but we're now squaring it for v squared, and that's over a. Now once again we can see that the mass will cancel, and if we divide through by g, we're going to get cos alpha equals g omega squared, sorry, I can't read my own writing, gu squared, no, sorry, get this the right way up, it's u squared, you're dividing through by g, so the g is on the bottom with the a, plus, and then we can see at this next part the g and the a will cancel to just give you 2 times the 1 minus cos alpha, so that's 2 minus 2 cos alpha. We can now take the cos alpha, 2 lots of it across the other side, and we'll get 3 cos alpha equals u squared over ga plus 2, and so then dividing through by 3 we get the following expression: cos alpha equals a third of u squared over ga plus 2. Okay, you might need to just work through that again for yourself just to check you fully understand where everything's come from and gone to. 5 marks, well again a method mark at this point for understanding you're using the radial forces towards the centre of the circle, and an accuracy mark for the correct statement. At this point, and expressing the fact that n is equal to 0 at the point at which the particle leaves contact with the surface. I'll give you a mark, and again a method mark for obtaining this next expression here with the alphas in place of theta and substituting the v squared term, and then for working through to the final expression correctly gives you the final mark. Yeah, and that's your 5 marks. Hope you found that solution helpful. For more assistance with your maths revision, please go to the Further Maths Support Programme website.